So getting into deep about these antenna design part, start from the scratch. So we can, as a first part, we can coin the topics as in this order. What is actually the antennas part? And for especially it is a biomedical applications, so I can talk about the textile antennas. I hope that the antenna paper, all of you may be handled or you have come across the antenna papers. So I'm directly going into the antenna design part because the area is a huge millimeter wave antenna design. So we have to start from the antenna design. So from the scratch we can start with the microstrip patch antennas actually. And the regarding the microstrip antenna design, next we have to go into the textile antenna design. So what are all the challenges in the textile antenna design, that also we can discuss, and how the antenna can be analyzed when it is embedded on the textile, and we can discuss about how the measurements can be done for these type of antennas, and what are all the applications that we can mention. So generally the microwave frequency is in the range of the above 1 gigahertz. Actually the millimeter wave range is above 18 gigahertz to 110 gigahertz. I think most of the colleges may have the measurement device for the microstrip patch antenna in the range of below 14 gigahertz only. But millimeter wave starting from 18 gigahertz, starting itself it is 18 gigahertz. Even the 5G as a subband is 6 gigahertz, but the millimeter wave technology start from 18 to 110 gigahertz. We cannot directly jump on to the 18 gigahertz. So as a part of the antenna design, we have to start from the microwave frequency ranges. So we can say that the microwave frequency range is above 1 gigahertz. I think the base we have come across as why this is coming under this very high frequency range. Generally, we'll say about the antenna frequencies are very high, or the communication we have entered into the high frequency communications. We know that the low frequency communication cannot be possible in the kilohertz and megahertz range. The problem is, as the Cooper has said, as the antenna size would be very large when we use the low frequency antennas for communication, right? This is the basic, right? The basic says that we know that frequency f, or we can say that lambda is equal to wavelength is equal to c divided by f, right? When the wavelength is small, frequency will be higher, right? When the frequency is higher, right, the wavelength we can say that it is very small. But for the low frequency, what will happen is wavelength will be large. Generally the antenna size depends on the wavelength. We know that half wavelength antenna, isn't it? Lambda by 2 antenna. So the lambda by 2 antenna of the low frequency, the size would be very big. For example, audio frequencies like 30 kilohertz to 300 kilohertz, that frequency, if it is transmitted without modulation, what would happen is antenna size would be of 75 meters, right? We can just calculate that c divided by f, and optimum size of the antenna is lambda by 2. So if the frequency is low, wavelength is large, right? That is the main reason we are going for the very high frequency. And also we can say that the dispersion, these attenuation and all, the high frequency attenuation is very less, isn't it? So the reflection is also very less. So the problem is we have entered into the high frequency. Go on, we are reaching the very high frequency bands. So the main point as a communication engineer, we can say that when the frequency is high, the wavelength is small. When the wavelength is small, antenna size is also small. That is why the mobile antennas are kept inside the packet. And for example, why we cannot stop with these lower gigahertz, right? And the another reason for going for the very high frequency, enter into the millimeter wave technologies, is the frequency is not sufficient. The bandwidth is not sufficient. Day by day, number of consumers are increasing. We cannot accommodate all the consumers in that frequency band. Slowly we have deviating from gigahertz range to the higher gigahertz range. bandwidth is high, right? All the attenuation problems are reduced, the path loss problem is also reduced. But the major problem you're talking about the 5G is the path loss. When we increase the frequency range, path loss is a main factor. That is a big ocean. Now we are talking about first is a microstrip patch antennas, right? Why I have said the 5G and frequency is the topic that we have specifically taken is a millimeter wave, right? So the millimeter wave frequency is a very high frequency range. From the scratch, we have to talk about above 1 gigahertz. When we are able to design the antenna for greater than 1 gigahertz, slowly we can enter into the high frequency ranges. As a first part, we have to start from the microwave patch antennas because all the 5G antennas, millimeter wave antennas, is a combination of arrangement of number of microstrip patch antenna as an array, right? It is a two-dimensional array. So that is why we are starting from the patch antennas, right? So the patch antenna is nothing but a metal patch on the top of the grounded dielectric substrate. It may be of any shape, the conventional or the rectangular, circular, and also the triangle, we can say. Actually, it is a very old invented in 1972 itself. After that, it has slowly has become popular, right? From when we collect the research papers, actually we have to start from the Munson paper, 1972, right? Everything is available in Indian Institute of Science, Bangalore. So when we talk about the biomedical applications, right, the wearable electronics is coming to the part. It may be in communication or security, or it may be in entertainment, games, or education, or healthcare. All are coming under these microstrip patch antennas embedded in the material, and we can say it is a wearable material. Application may be biomedical applications. So generally, typical type of microstrip patch antenna, it is shown in the top, right? This is the microstrip patch antenna, right? And there's a supply connector. There's a low noise amplifier is embedded in it. The power divider we have, and the how it is connected to the collimating lens. So it is a sample application. So when for the biomedical applications, we have to see the on-body antennas. So for on-body antennas, it has to be embedded on the material or the dress materials, and this is to be insensitive to the body proximity, right? The temperature changes on the body, radiation pattern, right? This will reduce the link loss. So these are the types of geometry we can use for on-body antennas. It's a simple microstrip patch antenna is a rectangle one, right? Rectangle in this is an inset feed. So these are the on-body antennas. This is the transient radio analysis when it is embedded on the dress material, right? It's a sample only I am showing it. We will see how we'll design the antennas. So when a material is a textile material has to be selected and the antenna is to be embedded on the material, and all the transmitter will be available, receiver will be available, and this can be tested with the help of the network analyzer how it is working. Then the transient radio analysis can be done with the help of this on-body antennas. So these are all the basic microstrip patches: rectangular, elliptical, triangular, it's a dipole material, circular ring. So these antennas can be designed with the help of the transmission line methods or cavity analysis method, or start from the Maxwell's equation. So Maxwell's equation that we have come across from the electromagnetic fields itself. So the Maxwell is a very famous equation. So we have four equations, I think, would know be del cross E, right? The equation in terms of you have a magnetic field, electric field and magnetic field. Generally, I would say about these Maxwell's equation as continuous time-changing electric field will create the magnetic field, and time-changing magnetic field will in turn create the electric field. That is why electric and magnetic field are continuously propagating in the space. One field will create the another field. Electric will create the magnetic field. Magnetic field will create the electric field. You have come across the Maxwell's equation del cross E is minus dou B by dou T. That is with the space equation and representation in terms of the displacement and the time is linked in the Maxwell's equation. He has proved that the wave is moving. Generally, all the concept can be analyzed with the help of the empirical analysis and the practical measurement that we can make. So empirical, nothing but theoretical analysis and the practical design we can make. So if we design, even the Marconi has designed an antenna at the starting, he has to prove that in terms of the empirical formula, the signal is transmitted. So he has proved that the signal which is generated in one side has to be transmitted through the atmosphere and it's reflected back and it is received at the other end. He has to prove it empirically how this can be done. That is why the Maxwell's equation has came into the picture. So when we can say that practically we can prove that the signal which is transmitted may be received at the other side. How we can prove it empirically? So the time changing field, right, will produce a displacement, right? At one particular second, the signal at one point, right? After a moment, the signal is moving to the another point. So there is a displacement from point number 1 to the point number 2, and also this time changing in the next second only. So t is equal to 0 second, the signal at one point, and t is equal to 1 second, the signal is moved to the another point. So the time is changing and also displacement is changing. That is the basic of the Maxwell's equation. Both are related. Del cross E is a displacement and time is nothing but dou by dou T is the time. So when we see about the Maxwell's equation, left side is what I can say that left side is the displacement and right side is time. So I think I wish to show you. Yeah. So this is what del cross E is equal to minus dou B by dou T. This del cross E is nothing but the displacement curl operator is leading to time changing operator, right? When one side of the equation is electric field, other side would be magnetic field. When the other side is magnetic field, right side will be left hand side is magnetic field, right side will be the electric field. So electric field will create the magnetic field. In turn, magnetic field will create the electric field. There's nothing but continuously it is happening, right? So one side is displacement, another side is time. So here the time and displacement is the relation between the two, right? This is the heart of the Maxwell's equation, right? Generally, all the analysis is started with the Maxwell's equation only. So this is nothing but a patch antenna. It is a very popular antenna. All the antenna people, right, start from the scratch. They will start from the patch antenna because the laptop antennas, now all the hotspot antennas, mobile antennas, everything is a microstrip patch antenna only. It has its own advantages and also the disadvantages there, even though this patch antenna has its own disadvantages. Advantages is more. So it is a metal patch suspended over the ground plane. It's a simple air-filled insulated space patch antenna, right? It's from the ground, air is filled. That is why it is an air-filled insulated. A patch antenna consists mainly of a square conductor mounted over the ground plane. The dimensions are roughly half wavelength. It is lambda by 2 wavelength. Excuse me. the insulating space between the two planes may be air. Here, that is the example it is shown. So this is the basic construction. We can understand base is the ground and the gray color is the dielectric material. Over that surface, it is a microstrip patch antenna. It is printed. So generally, the patch antenna is a conducting material of particular length and width. There is a formula to calculate the length and width of the antenna, and with the help of the particular feeding method, we can join the feed line like this, and the height of the dielectric material is a small h, and its dielectric permittivity is epsilon r. And the very important parameters for the design is selection of the dielectric material and its own permittivity. Excuse me. Yeah. So the design consists of length, width, and the selection of the dielectric material and the height of the dielectric material. So the very important thing, the design is the selection of dielectric material and its height. In the market, it is readily available the different types of dielectric material and its own thickness. The length and width of the microstrip patch antenna has to be calculated. So the base is the frequency or the wavelength. So from that only we have to start the antenna design. Because the application is different, the wavelength and frequency will be different, hence the wavelength will be different. Generally, when it is loaded with the dielectric as a substrate, the length of the antenna decreases as the dielectric constant increases, but we cannot, beyond the level, we cannot increase the substrate. It has its own fringing effects. This is an array of circular patch antenna. It's a two-dimensional physical geometry. Its shape may be of a basic is a square, circular, rectangular, elliptical, like that. This is a circular type of conventional antenna embedded on the dielectric material, which is a two-dimensional array. So this is an application for the UHF ultra high frequency range. The size of the antenna is tied with the wavelength because of the resonant frequency. So generally, why we have to prefer a microstrip patch antenna, right? So it can be a low profile antenna, conformal, any shape we can fabricate, right? It may be in bent, can be embedded on a textile material or hard material, hard dielectric surface, right? So it is a very low profile antenna, and fabrication is easy to fabricate. Even as a lab mini project, we can fabricate the antenna in your own place itself without any additional purchase of the equipment. We can fabricate. It's very easy for fabrication at the cost of even 1000 rupees. You can etch the antenna with the help of the photolithography process in the laboratory itself. And the feeding method is also very easy because coaxial cable, it can be suited, or we can go for the microstrip line. But you can fabricate that feeding itself. Microstrip line also we can merge with the antenna design. And very easy to fabricate an array also, and it can be incorporated with other microstrip circuit elements. You can easily incorporate with other circuit elements. And the pattern is hemispherical because we are considering over the ground plane. So the antenna is exposed over the surface, hence the radiation pattern is hemispherical, because we would not encourage the radiation pattern below the ground surface, right? Always there below the ground surface radiation is possible, but we will stop with the help of the ground plane. we can have radiation above the surface of the antenna. Directivity is general, it is moderate 6 to 8 dBs, and the minimum 6 dB we can achieve for a simple microstrip patch antenna of rectangular in shape. If the shape is properly tuned, we can go for a moderate 8 dB directivity, and also we can achieve the gain. So the textile materials can be used as a substrate material. So without directly going to the textile antenna, some more points we can discuss with the help of these uh, microstrip patch antennas. Yes. So for geometry of the rectangular patch, I want to discuss with you, because when any person start with the antenna design, this is more useful. So L is the resonant length dimension. Width of the antenna is, we can assume that it is W. It is usually larger than the length, right? So the W is less than 2 times that of L, or 1.5 times that of L. It is possible. And the feeding, right? If this is the dielectric surface, from the ground plane, the antenna can be fed with the help of the coaxial feed at any particular point. The point of the feed has to be selected with the help of the formula. By substituting the length and width, thickness, everything, we have to calculate at which particular point the feeding has to be given. Right? So when the point is selected, we can feed the coaxial cable. The coaxial cable is also very, very cheap. We can purchase even 50 to 100 rupees. The connector points. So the coaxial connector, then we can connect the coaxial cable. So simple coaxial feeding, the resistance we can calculate with the help of the position at which particular point the antenna has to be supplied with the help of the supply voltage. But the difficult point is also the same, obtaining the proper impedance matching for thicker substrate, because the probe has its own inductance. So the selection of the feed point is more typical. Otherwise, it will create a probe radiation problem. That is also has its own disadvantages, right? This is produces a spurious radiation from the patch antenna, and it has its own surface wave excitation also. There's a microstrip line feed called the inset feed. The conducting line has the extended at the tip. So we can connect the connector at the end point. Instead of the coaxial feed, microstrip line feed also we can do. And another one is the probe fed. That is also easy to fabricate. You can obtain the match by controlling its position. It requires a hole, wire hole. In the design itself, even the CST or ADS or any antenna design software you have, you can design the hole and we can select a position. It is an aperture coupled type of feeding method. It has its own broader bandwidth, but it is somewhat compared to the other techniques, its fabrication needs a good idea about the feeding method. It has spurious emissions is possible. This is called the inset feed. The antenna, this same copper is extended outside for the inset feed. This allows for the planar feeding. There's more advantageous one actually. Very easy to obtain the input matching. We know that for all antenna, you have its characteristic impedance, right? The characteristic impedance role is very, very important for the communication point. The whole world lie in the characteristic impedance. If the cable impedance is not proper, right, the signal cannot be derived. And if the antenna impedance is not the equal to the cable impedance, whatever the power supply you can give very good antenna design, the signal will not be fed into the antenna, right? So here the calculation is the length and width of the inset feed line. At this point, the antenna impedance has to be properly matched. Then only the current can be excited with the help of the inset feed. So it has its significant radiation because of its thickness. The substrate, the thickness, major role. Then there is a proximity coupling by giving a microstrip line at the middle, right? It's suitable for the planar feeding, but less line radiation compared to the microstrip feed. This is good proximity. That is EMC coupling. So you can go for the multi-layer fabrication. This would be suitable. Again, the matching is very important problem. Gap coupling is also another method of feeding, suitable for the microwave full wave designs. This also aperture coupled patch used for the planar feeding. This also used for the multi-layer fabrication. Equivalent circuits, how to design a different type of coupling, because the antenna is as its own equivalent circuit, and also the feed is also having an equivalent circuit. So all are lying in the resistance, inductance, capacitance and conductance. We can convert our material into an equivalent circuit or find an equivalent circuit, then convert into a planar structure. So probe has its own feed loss, efficiency and all. We will go into a particular design of rectangular antenna. So the cavity analysis method, resonant cavity analysis method is used to design an antenna. We'll start from the resonant frequency, how it is created and how we can select the particular frequency with the help of the length and width. So first of all, we have to say the rule of thumb for the calculations. A microstrip antenna, what are all the design equations? For efficient radiation, what should be its length and width for the particular selected frequency, right? So this is the base for an antenna design, right? The participant, you please just you can see the equations. I think surely you will understand. For efficient radiation, width of the antenna W is nothing but the velocity, free space velocity V0 divided by 2 times that of the resonant frequency F, or root of 2 divided by epsilon r plus 1. See this equation. What are all the parameters? Width. Width is equal to, that is depends on the resonant frequency, then dielectric permittivity of the material, right? You know the structure of the antenna, ground plane, over that the dielectric surface, right? Just I'll show it to you. Ground plane, dielectric material, over that the conducting patch. This is the construction of the simple rectangular patch. We are going to calculate what is its width and what is its length, right? And what should be the height and what should be the dielectric permittivity, right? So the selection depends on the dielectric material. Dielectric material selection depends on the frequency which we are going to use. So as a first point, what we have to say about the frequency based on the application. What is the application that we are selecting? Based on that only dielectric permittivity has to be selected. Okay. So we know the dielectric permittivity and we know what is the frequency of selection, right? So based on that only the width can be calculated. So what is the width? Width, you see, free space velocity 3 in 10 power 8 divided by 2 times that of the resonant frequency, root of 2 divided by epsilon r plus 1. Okay, good. W can be calculated easily with the help of simple calculator. Then what should be the length? Length is nothing but, right? So 1 divided by 2 into F, or root of epsilon effective. Epsilon effective has its own formula with the help of epsilon r1, the last formula you see. epsilon or effective, and this is C, or C divided by, we can say that C divided by 2 into F or root of epsilon effective, or instead of C we can say that 1 divided by root of mu naught epsilon naught. 1 by root of mu naught epsilon naught is nothing but free space velocity C, 3 into 10 power 8. So the differences from the length and width you see, only the differences, this is again C divided by or V naught divided by this one, but here directly uses epsilon or permittivity, but this one uses a epsilon or effective permittivity. So effective permittivity has to be calculated from this epsilon or effective is equal to epsilon or plus 1 divided by 2 plus epsilon or minus 1 divided by 2 within bracket 1 plus 12h divided by W, the whole power minus 1 by 2, that is in the denominator it is root, or 1 plus 12h divided by W. What is h? Height of the dielectric material. W is the width of the antenna, right? First the width is calculated. After calculating the width we can calculate epsilon or effective. Okay, minus, see this formula now, the L depends on this term, minus 2 times that of del L. Del L is the fringing length. Because of the radiation, there will be change in the antenna length, not the physical length. Effective length would be changes, right? In the antenna concept, you have come across the effective height of the antenna, isn't it? Physical height and effective height is different. Similarly, here the physical length and the effective length is different. All the length, physical length cannot be utilized as an effective length. May changes, slight variation would happen. So that due to the fringing field outside from the top surface to the dielectric material. So this del L, it has its own formula. Again, it deals about epsilon or effective, then W, H, all those things. Now this would be the del L. Now after calculating del L, we can substitute in the capital L. So width calculated, length calculated with the help of the del L, epsilon or with the help of epsilon or effective only L we can calculate. This is the simple design equation of microstrip antenna. Anybody, you can start with this calculation. Bandwidth is directly proportional to the width, right? So after calculating the width only, we can talk about the bandwidth, right? A simple selection as shown here, a sample calculation, and the inset, the point at which particular point the antenna has to be fed, that should be calculated with the help of the impedance only. This is an efficiency, radiation efficiency, total radiated efficiency by total efficiency is nothing but the radiation efficiency. Different types of material for the foam substrate, and generally available in the market is derived material. It is epsilon or 2.2, or the in terms of a 2 to 4 range we can get from the market the substrate materials. The thicker would be the substrate, it will be better for the dielectric losses. So this is the radiation pattern. For particular epsilon or value, the radiation efficiency is maximum when this ratio H divided by lambda naught is approximated to 0.02, right? And this will be the radiation pattern. Just I'm showing you how the radiation pattern will look like. A microstrip antenna has a radiation pattern like this. E plane, we can draw the radiation pattern with the help of the MATLAB. Even with the help of the MATLAB also, you can write the MATLAB program and we can construct the E plane radiation pattern and H plane radiation pattern. It will look like this one. How this graph is attained? That is nothing but with the help of this equation. Electric field, when the far field radiation pattern, if you apply in the loop of hemispherical the value of theta, this r theta side would have come across. theta is the elevation angle, psi is the azimuth angle. If we substitute theta is 0 to 180 degree and psi is from 0 to 360 degree, we'll be getting in the for loop, in the MATLAB for loop we can construct, and you can write this equation in the MATLAB, and you vary the theta and the psi value. R is the radiation from the origin point to the point of antenna position is kept as an R. Width you can substitute, length you can substitute. If you implement this function, a simple function even in the MATLAB, you can get the radiation pattern of E-plane pattern like this. These are all the computer aided formulas you can use. So, what is the problem in the microstrip patch antenna? Compared to the advantages, very less the disadvantage only that we can overcome with the help of the variations that we can make in the microstrip patch antennas. Generally, it is a low bandwidth. That is why we are doing many things to increase the bandwidth. Creating a slot over the antenna, U slot or a F shape of antenna to increase the bandwidth, because the microstrip patch antenna is a narrow bandwidth. So, in order to improve the bandwidth, we can do many changes in the structure of the microstrip patch antenna, and also the selection of the dielectric material. But efficiency is also less. It is limited by the conductor and the dielectric losses, it is sure, and by the surface wave also, because these are the hemispherical radiation pattern. This is going to be held over the surface of the antenna, so there will be a surface wave loss. It is severe when for the thinner substrate. That is why the proper dielectric material has to be selected. For improving the bandwidth, you can go for the L-shaped probe or top hat on the probe, or selection of the, you can improve the bandwidth with the help of many types are available. Strip, slot, foam inverted patch, inverted F antenna, that is for the laptop antennas. We can use inverted planar F. We can select, we can increase the bandwidth by 25%. And the slot is introduced in this point. We can have many number of layers which we can construct with the help of the stacked patches. Low permittivity antenna, triple tuned resonance. We can use the probe feed. So this is a stacked patch with the help of the ACP fed minus 10 dB. S11 bandwidth is about 100%. Is a S11 curve, return loss curve for the measured and also the calculated, simulated and the measured results. O base. The bandwidth is actually increased with the help of this stacked patch. See, this curve is more important for antenna testing, right? So first, after, for example, the frequency is selected, okay, length and width is calculated, proper dielectric material, with the help of the proper dielectric material, and the height of the substrate is selected. So after calculating, we are fabricating it, connecting connector over here. We have to test the antenna whether the antenna is working, right? So conducting material, this is nothing but conducting material. Over that, it's a stacked patch antenna is fed, and it's a rectangular. The top surface is the metal rectangular antenna. This is a square. This one shape is a square microstrip patch. Below that is a stacked patch with the foam. For the testing, first we have to test the antenna with the help of the um, network analyzer. So the network analyzer will measure all the S parameters. So the S parameter can be measured for the antenna is S11. Antenna is a single port antenna. So S parameter will be only 1. S11 will be the S parameter for the antenna. That can be measured. This is the curve that we are getting with the help of the network analyzer or maybe in the simulator. If they design the antenna in any software like CST or ADS, then we will get an S11 plot like this with a return loss in decibels. So the antenna result would be like this. If you plot the x-axis is the frequency, y-axis is the return loss, that is S11 in decibels. Right, 20 log of this S11 is nothing but the return loss. It would be like this. So what is the meaning of this curve? What is its statement? Without the stacked patch, a simple antenna will have only one depth point like this. You have only one depth point like this. Here this one has stacked patch, that is why you have two depths. So what is its purposes? Because the idea is to increase the bandwidth. Here the bandwidth is increased. How can I say that the bandwidth is increased? See, 0, minus 5, minus 10, minus 15, like that it goes on. When the antenna would be good, the return loss is less than minus 10 dB, then only the antenna is operating in the specified frequency ranges. Minus 10 dB or at least minus 14 dB level. So minus 14 dB level, if you draw a line in this point, minus 14 dB, you see these frequencies starting from this up to this point, right, we will be getting below minus 10 dB, right, or 14 dB, minus 14 dB, this line, right. So when it is minus 14 dB, less than minus 14 dB, the antenna is working, meaning is 95% of the transmission is possible, only 5% is reflected back. That is what the meaning of below minus 14 dB. Minus 30 dB, 35 dB, 36 dB and all is 99.999%. It is transmitted. Only very few reflection is happening, right? If you achieve minus 14 dB level, right, that would be better. So here the bandwidth you see, when you extend the line to this x-axis, it would be even this point. So 5.2 gigahertz to 9, approximately 9 gigahertz is the bandwidth of this antenna, right? This stacked patch antenna has its bandwidth as 5.2 gigahertz to 9 gigahertz, very wide bandwidth. If suppose this curve is not there, right? So or this area not is there, not for the stacked patch. When this is a simple rectangular patch, what will happen is draw a 14 dB line from this point, extend below 5.2 to below 5.8 would be the bandwidth of the microstrip patch, right? So if you do any modification in the structure to improve the bandwidth, then only the bandwidth can be improved. Otherwise, microstrip patch antenna is a low bandwidth antenna, right? So we can increase the bandwidth by doing some modifications in the microstrip antenna. Okay. And this we can talk about the Smith chart also. So when you draw the Smith chart, the center point has to be reached. Center point is a match point of the Smith chart, that is S is equal to 1 actually. So even you have a zero reflection coefficient is 0, 1 plus k by 1 minus k is nothing but S. So when the k is equal to 0, S would be equal to 1. When there is no reflection, standing wave ratio is 1, right? Standing wave ratio variation is starting from 1 to infinite. So minimum standing wave ratio is 1, for reflection coefficient 0. When you draw the curve for S11 for the Smith chart, if you draw it, the impedance matching, you can test for the different frequencies. What would be the standing wave ratio that we can check? There are so many factors we can go for improving the bandwidth for the parasitic patches. We can go for different type of edge coupled, all those things to achieve the bandwidth. We can increase the bandwidth by making a slot over here. When you make a slot, the slot will work in the another frequency band. So the combination of the metal strip and the slot will operate in the significant change in the bandwidth, right? 10 to 40 percentage of the bandwidth is increased because of the double resonancy effect. All or the paper results only. We can make double U slot or E patch, F patch. So a number of materials are there to increase the bandwidth. So these are all the antenna structures. E band, that is multi-band antennas. The shape you see, if you prefer a different shape of the microstrip patches, each and every area will work for the different bands. For low band, high band, right, it will cover the combination of these bands would result at the different band frequencies. So combination of the different band would result in the wide bandwidth. So now the narrow bandwidth problem of microstrip antenna can be eliminated with the help of the different structures, the shapes. But to cover the very high frequency ranges, you have to go for an array of antenna, not the multi-band antenna. These structures would address a problem of increasing of the bandwidth with the help of the single antenna only. The single antenna will work for multiple band of frequencies. Miniaturization is also possible. A high permittivity, quarter wavelength patch, that is lambda by 4. Planar inverted F antennas, PIFA antennas are also very famous for the design. Capacitive loading effects can be created. We can go for the slots and meandering effects. So I'll show you what is its miniaturization. The size can be reduced by increasing the dielectric permittivity. So epsilon r is equal to 1 and this is epsilon r is equal to 4. Size would be reduced, like W is changed to the W by 2, L is changed to L divided by 2. Right? Half of the shape is reduced. Quarter wave patch, small quarter wave patch. Excuse me. This is planar inverted F. For miniaturization, this is capacitive loading, planar inverted F antenna. Excuse me for a minute. the slotted patches. This is called the meandering effects. So, for example, you have come across RFID antennas. These RFID antennas will use the meandering structures. There is a meandered square wave patch antennas, meandered PIFA antennas. There is a side view and top view of radiation is improved with the help of the surface wave excitation. There is RSW antennas. These are all the meandered antennas. This is the project's works of the PG students. Meandered structures is so simple. The formula calculation only we can implement the theoretical calculation with the help of simple any software language. Then the calculation can be done over the CST or any software, antenna design software. Then you can implement in the software and we can create the return loss curve. You analyze it, then we can fabricate the simple as a mini project, and we can see the radiation pattern. We can fabricate and test the return loss curve, and the radiation pattern we have to go for the anechoic chamber. This is the meandered antenna. See the RFID structures, even these antennas can be implemented for the RF tags. RFID tags, you know, for the car number plate and for the toll gate payment. These type of meandered structures will be suitable. The broadband shorted patch antennas, different types of antennas I am showing it to you. Any type of antenna we can select and we can work for the microstrip patch array antennas. When we work a simple antenna, then we can go for the array of antennas. This is the array of antennas, series fed or parallel fed, corporate fed. Right? This is a series fed, one antenna will fed the another. So continuously it is fed, but this one is a corporate fed. All its own advantages and disadvantages. This is the parallel array, power divider to feed the power. The one-dimensional array. This is the parallel feed of two-dimensional array. This is an example of the millimeter wave antenna. See, now can you understand why I am saying a single antenna design is also important? So, in this antenna array 16 by 16 elements, single antenna is a microstrip patch antenna. It has its own feeding type, right? When the single antenna is designed, right, we can just copy and paste the remaining antennas. And the another problem is feeding. Feeding point, see, the feeding is 4 antennas are grouped. Microstrip fed is done. Nearby next 4 antennas, microstrip fed is done. Right now you take these 4 antennas, and the lower one, next lower 4 antennas. All are connected with the help of another feed. Right? It is a feeding line will supply these feed insert feed. Similarly, it will go extend to the center point. You see, from the center point, the lengthier feed will select into the 4, then 4 again split into 4. Like that, it goes on. This is nothing but a parallel fed antenna. It's an example of a two-dimensional array. When the antenna is a two-dimensional array, this would be concentrating the power only in a particular direction. Single antenna has its radiation pattern as a broad, right? Array of antenna, the radiation pattern is sharper one, right? When the radiation pattern is sharper, you can track the signal to any point. Broad radiation pattern descends, a single antenna will cover the 60-degree half power beamwidth. But for the present day applications, for long distance, unnecessarily we have to transmit the power in other direction. We have to transmit the power only in the particular degrees. If we know where is the receiver, we should not waste the power by sending the signal in all remaining directions. That is why the gain has improved, half-power beamwidth is reduced, hence the directivity would be increased, right? This is a scanning array. A number of antennas are connected. The back side of the feed point is shown. Power divider is also the design like microstrip structures. We have to design a power divider for the supply, phase shifters to connect the excitation and also the phase magnitude and the phase excitation properly fed to the antenna. Then only it would be a scanning array to transmit and receive the signal in a particular direction. It's a reflect array, feed point, high gain, but it is low bandwidth. It is small in size. The dimension is shown with the help of the scale, long scale. Telemetry antennas, see it is a planar structure. It is shown in this, and this how many number of elements you have. 8 elements are arranged as a series fed, right? And here it is a corporate fed, seriously arranged, but it is fed with the corporate fed, and it is conformal about the cylinder for telemetry applications. Return loss you see minus 45 dB, at least reaching to minus 40 dB, and below minus 10 dB starting from this point in the range of all the biomedical applications. ISM band of 2.45, but here it is working from 2.18 or 2.2 to 2.3 it is working. The lens coupled printed antennas. We'll go for textile. Now, something we discussed about the antennas. What are all the feeding methods? What would be the return loss? When for the biomedical applications, the antenna would be, the substrate material should be a textile materials. The fabrics should be wearable, durable, and it should be flexible. So the proper textile material has to be selected with a known dielectric constant. You can ask a question that how the dielectric constant can be measured. There are numerous methods are available even in the physics laboratory to measure the dielectric constant value. Even for any material, make a powder type of material and insert into the rectangular waveguide structures. Excuse me for a moment. Saravanan sir.
மேடம் உங்க மெயில் ஐடி வந்து ரெண்டுமே இருக்குது மேம். ஜிமெயில் இருக்கு, பிஎஸ்என் இருக்கு. சரி விட்டுறலாம்
குரூப்ல சரி.
Excuse me, ma'am. Meena, ma'am. I have muted you, ma'am.
Excuse me, ma'am. Meena, ma'am.
Yes, sir.
Ma'am, you since your phone conversations were
Okay, okay.
audible to us, I have
Okay.
muted you, ma'am.
Okay, sir.
That's why. Okay, ma'am. Thank you.
So the textile materials can use a substrate material as nothing but a part of cloth. So what actually discussing about is how to calculate the dielectric loss calculations, dielectric material selection. We can select any dielectric material, and there are many numerous methods are available to in even in IITs and IIT Kanpur, IIT Chennai, and also in the laboratory, we can do on the microwave bench itself to measure the dielectric constant. Whatever the material that we have chosen, we can calculate the dielectric constant epsilon r. Or the known materials, the electric constant known materials are there in the market that we can purchase as a substrate material for textile, which will reduce the surface wave losses and improve the impedance bandwidth of the antenna. So what are all the factors which will affect the textile antennas is main the permittivity and also the loss tangent del parameter. The dielectric property depends, this depends on the frequency, temperature and the surface roughness, moisture content in the material and the purity of the material, right? This depends on these factors. What are all the design issues? The calculation of the dielectric material value and the selection of the height. Even textile material have its own 0.8 millimeter to 0.6 millimeter thickness be suitable for dielectric material. And by first we have to select these materials, then what are all the antenna parameters is must to calculate is a return loss, VSW or standing wave ratio, impedance, gain, directivity, bandwidth and the quality factor. So generally these textile antennas would be suitable for medical health care, and then also the sports witness monitoring purpose, military and also the security. So first we have selected as a title of the selection is only for the biomedical applications. So we can see the medical health care, how these antennas would be used for the medical health care. For that, how to fabricate these and what are all the challenges when we design the textile antennas and material selection. So regarding these, for the next half an hour, we'll see how the textile antenna would be suitable for biomedical application. Next, we'll go to the um, what the measurements part we can discuss. And the textile antenna structure, it has own high directivity, ease of construction. You have the types is partial textile patch or maybe in fully textile patch antenna. So difference between partial and fully is a partial textile patch is nothing but the textile higher dielectric material is a textile material, but the conductor and the ground plane is the conducting material like copper. Copper ribbon tape we can purchase, we can use it as the conductor and the ground plane, that is partial textile patch antenna. Fully textile patch antenna is all the material we can go for the textile, even the conducting material itself it is a textile material we can select. It's a simple microstrip patch, we know it. This also the main formula that you already know it. So the width of the patch, effective dielectric constant, length we have discussed. Del is the fringing length, that will be the effective length. What is its feeding? Characteristic impedance calculations. 50 ohm microstrip patch antenna transmission line can be calculated with the help of this SZT formula. So all the design equations we already know it. The ground dimensions, right? These slides and all I'll share it to you. So regarding, for example, this is the work of the PhD. The various microstrip patch textile materials has its own dielectric material selection. Different textile materials with the dimension in the minimum, that is in the millimeter dimension, it is written. For example, a denim cloth, the textile material is a denim material. We have calculated with using these formulas and all, calculated the width, the length, inset feed, everything, feed length, feed width, ground plane, ground length, everything. So for the different material we have calculated. So the different textile materials are the denim, maybe cotton, flannel materials, all are available in online. Polycotton, 12 weave, polyester materials is calculated. Now, how we have to select the textile? What are all the criteria that is based? Permittivity, loss tangent, dielectric, textile thickness, humidity content available in the clothing, and the surface resistivity. Then ramp mechanical deformations for conductive and the textile, dielectric textiles. So, how the dielectric material selection is possible with the help? So, in the internet itself, it is readily available for the different textile materials. What's its permittivity? For you can see, and from that, anyone we can select. For example, denim textile material. These are all the properties. The types of textile material is given epsilon r value. For example, denim textile material permittivity is 1.6. If we purchase that, it's a denim material, the dielectric permittivity we can use it as an 1.6. For the thickness of H is 0.15 millimeter. So a material, a clothing material, 1.6 dielectric permittivity, then 0.15 thickness, and the loss tangent is tan del is 0.01. Similarly, different material, what is its permittivity, what is its thickness. You can purchase any material and we can use this data. And the conductive material selection. So conductive material selection is for the microstrip patch, right? This is for the dielectric. The microstrip patch is conductive textile material is nickel, copper, ripstop fabric. Now the conducting material itself, it is a fabric, it is a copper. Then shielded super, it's also another conducting material. And the pure copper polyester taffeta fabric is also a conductive textile material. Is a conductive non-textile material is simple copper sheet we can use, or copper foil tape is readily available in, even in online you can purchase copper foil tape with conductive adhesive, because you have to paste it on this textile material, you know, ground plane, dielectric, and over that a conducting surface. If it is a non-textile material, you have to paste that material copper sheet over the textile. So you need an conductive adhesive to paste on the clothing material. So you can use a copper sheet, you can stitch it, or you can paste it. So there are two types of conducting material: conductive textile and conductive non-textile material. So for these materials and all, there's nothing but the surface resistivity, different types of conducting materials, conductive non-textile materials. All are the different materials has its data sheet. Conductivity, conductive element, what is the conductive element, what is its thickness, weight and all. Then with shielding, suitable for which one, all those things is readily available. So what are all the study? Sorry for the disturbance. There is a connection has dropped.
Yeah, ma'am. We
Ah.
could.
So these are the different types of conducting materials we can select, and these are all the data sheet available in even in the internet, and we can collect it. So the surface resistivity, conductivity, because these data and all is required to for the calculation of antenna structures design, whether it may be in textile material or non-textile material, suitable for all biomedical applications. So for the textile antenna, what are all the main factors that would affect it? Human body interface to the antenna performance, bending of an antenna, antenna return loss, radiation pattern, divergence, specific absorption rate, SAR modeling, then water absorption. So regarding the human body interface to the antenna performance is when we connect the textile antenna in the jacket of a man, so the human body interface will be a major problem. That is also we have to analyze. And bending of an antenna based on the location of the antenna fixed on the shirt, so the bending would happen. So even in the testing that we have to test the all the S parameters, the radiation pattern and all, by including the bending also. The general return loss would affect, sure. Radiation pattern of the antenna is also the necessary basic study. Divergence is another parameter. Specific absorption rate that we have to model, that we can do with the help of any software analysis. Water absorption rate is also a very must. So what are all the analysis, sample analysis, I'll show it to you. Then you will move to the measurement part. A sample is the denim material is taken, substrate material is the denim, conductive material may be of any type is compared, copper sheet is selected. These are all the conducting materials available. First two is in non-textile, the last three is a textile material. The frequency for all or the ISM is taken, example, medical band. So the frequency is the operating frequency, and you see the voltage standing wave ratio all are nearing to 1. Surely the standing wave ratio should be near to 1, should be lower than 2. And the return loss should be greater than minus 14 dB. Yes, this is minus 14 dB exactly. And this is minus 28, minus 29, 20, minus 16. All are greater than minus 14. Then the impedances all are nearing 50. Excuse me. So different materials, different frequency, but the frequency range is selected as a 2.45 actually, but all are not working for exactly 2.45. This frequency is mentioned as what is the dip it is shown in the return loss measurement, that is what is returned. And the standing wave ratio is generally it is 1 to infinite, which is suitable closer to the 1, which is very good. It should be less than 2. And the return loss is all are less than minus of 14 dB only. So minus 28, 29 like that goes. And impedance is approaching, it is all are the characteristic impedance 50. Last one is not suitable, so 36.7. So what are all the material which is best suitable is colored. So CFT material is best suited because it is range is compared to the copper sheet, this would be better, and for the textile material the NCRSF is suited because it closer, the frequency range is also closer and the return loss is good. So based on the analysis that we are making, right, like this, we can select any textile material and conductive material, then calculate all those things. This can be done with the help of formula, and also we can go for the measurement. So for the antenna part, we have to do the calculation, measurement. This both has to be matched perfectly, then only the design is okay. Analysis can be based on by seeing the results of whether the frequency dip is available in the particular range of frequency, standing wave ratio is suitable, return loss is suitable. Analyze different materials or select only one substrate material, one conducting material, then you apply it and change the shape of the antenna, and we can test the same frequency, VSWR, return loss, everything for the same material, right? Anything can be done. This analysis actually made to select which textile materials would be suitable for biomedical applications. The result of the work is shown here. It cannot be done directly by selecting any one of the material. We have to select the material and analyze the results of the material which is selected. Then only we can use that for radiation pattern testing, because the radiation pattern testing is costly. Starting from 5,000, it is varying. So the textile antenna fabrication is very cheap, but the analysis that we are making, testing, is little bit costly. Return loss we can measure with the help of any network analyzer. For this frequency range, it is medical band, so it is 2.45 gigahertz. We can use below 4 gigahertz network analyzer for the measurement. But for the millimeter wave antennas and all, above 18 gigahertz network analyzer we need to measure. As an analysis of any biomedical application antenna I have shown to you. Different types of antennas are available. Cotton, textile, we can compare the results by analyzing it, which would be suitable for which application, that's all. Now I want to discuss about the measurement part, because the title coined is antenna design and also RF measurements for biomedical applications. Some basic concept I would like to mention for the next part. The power definitions. So what are all the basic needed for the RF measurements? Generally, we would say that the power measurements is with the help of the dBm. So dBm is decibel per milliwatt, 1 milliwatt. That is what 10 logarithm of the power which is received with respect to the 1 milliwatt of power transmitted. You see all the applications, the tower applications and all the power level represented with the help of the dBm only. So the transmitted power would be considered as a 1 milliwatt. 1 milliwatt is 0 dBm transmitted, right? If you transmitted 100 milliwatts, this would be 20 dBm. Just we can substitute in this formula, we will get it. If it is 1 watt transmitted, it is 30 dBm, right? So generally, example is see here, it is minus 110 dBm. This much of power, it is minus 110 dBm is nothing but 0.401 nanowatts. Why especially minus 110 dBm is given is the mobile power is minus 110 dBm. Ranging from minus 110 dBm, 120, even minus 120 dBm can be received with their mobile phone. So for the 50 ohm load, you have a minus 110 dBm, right? It is 0.7 microvolt, we can say. Right? So this is the power level required. So for all the power in the antennas, we will refer only dBm, not the decibels. It's a very important concept about this dBm is the dBm and the watts. We will represent with the help of the 1 milliwatt of power. When it is 25 milliwatt of power received with the help of 1 milliwatt transmitted is 14 dBm is the power level. It is a standard. See, what is the typical value which is selected? Generally, you see 4 dBm is 2.5 milliwatt. So, the power level is decided for the different applications. Bluetooth standard, class 2 radio, the maximum signal power for the wireless network is minus 10 dBm and all. For all the wireless signal over the network, it is minus 70 dBm. For the GPS satellite, it is minus 127.5 dBm. It is a femtowatts. The power is femtowatts of power, because we cannot simply increase the power level. So the wireless LAN we can increase to the 100 milliwatts, to 70 to 100 milliwatts we can increase. But for the GPS applications and all, we can go for only femtowatts, minus 0.178 femtowatts. We know the electromagnetic spectrum ranges from lower to the higher range of frequencies, extreme high frequencies, and this is the frequency versus time domain analysis. So as an electronics engineer and RF engineer, we should know that what is the time domain measurements and what is the frequency domain measurements. Generally, for the lower labs, lower semester labs, we would use a CRO for all the measurements. For the voltage measurements and even the frequency measurement, we will use with the help of the oscilloscope. But for the high frequency ranges, we will not go for the oscilloscope measurements. We would go for a spectrum analyzer measurements. What is the difference between the time domain measurements and the spectrum analyzer measurements? Time domain measurements is a single signal as taken, showing a signal like this. We can, how would you measure time in the oscilloscope? With the help of the time, you will measure the frequency. So x-axis would be the time, y-axis will be the voltage. In the time measurement, we will measure the time and we will calculate 1 by t is the frequency. We can directly calculate the frequency from the time domain signal. But for the frequency domain, you see, you can measure number of frequency component with the help of the spectrum analyzer. This is what you are seeing it. One signal, second signal, third signal. So you have your own 3 frequency measurements is possible with the help of the spectrum analyzer. We can directly measure the frequency. Here, x-axis is the frequency, y-axis is the power for the spectrum analyzer. But in the oscilloscope, what is the difficulty? You can see only one time signal. But here you see many number of time signals in terms of the frequency. You have 3 signals, 3 frequencies, right? How many signals? That is equal to how many frequencies? You have 3 signals, you have 3 frequency components, you can see it. For example, where is the application? After modulation, you will be having many number of frequencies, isn't it? A single sinusoidal signal will have a single frequency component. But after modulation, you have many number of frequency component present in the signal. For example, in amplitude modulation case, you have a message signal and you have a carrier signal. After modulation, you have a modulated signal will be present. The modulated signal has its components of carrier signal, message signal, excuse me. I'm sorry. The frequency measurements, you see, you have number of frequency component present in the modulated signal. So in the modulated signal, you have a carrier frequency FC and FC plus FM, FC minus FM, lower sideband and upper sideband, first sideband. Second means FC plus 2fm, Fc minus 2fm, then Fc minus 3fm, Fc plus 3fm, like that it goes on all the side bands, right? So you have a left side band and also you have a right side band. You have an upper side band and lower side band in addition to the carrier signal. So you have number of frequency component would be present. For in our subjects, what you would do is you will consider only the first side band, lower side band and upper side band only. The remaining or the spurious emissions that's happening from the circuit. You will generally avoid it with the help of the filter. You will remove all those. Why you are removing is the magnitude is very less, V square divided by R. Then that power is slowly reduced in the side bands, right? When you read about this communication theory paper, you understand about what are the amplitude of the side bands. So goes on, it is decreasing when it is coming from the left hand and the right side. The power is reduced. So maximum will select the first lower sideband and first upper sideband only, right? LSB and USB. So you have minimum 3 frequency component will be selected for after modulating a signal. So now all the signals are modulated signals only. So you cannot measure a modulated signal with a simple CRO because it is showing only one time signal. But actually we are using it for the modulated signal testing, yes. But the students will say about that it is more distorted signal. The signal is not coming. And for example, delta modulated signal. It is very difficult to see the delta modulated signal in the CRO. Because CRO is doing with the help of the superheterodyne receiver inbuilt inside. It will capture the signal at only one request rate and it will pick the signal and it will show it on the screen. If there are number of signals is present, all are time fixed in the one time scale. But the spectrum analyzer is tuning its own frequency. It is producing its signal on the screen with multiple frequency components as a thin line in the y-axis. You have 10 frequency component as present, 10 frequency component will be shown to you on the screen. It is tuned in such a way that to produce all the frequency component on the screen, right? Now can you understand the basic of the oscilloscope and the spectrum analyzer? So oscilloscope will be suitable only for time domain measurement of a single signal. It's quite okay. But for the many number of frequency components, you cannot see it on the oscilloscope. You can see it only on the spectrum analyzer. You need a spectrum analyzer to see multiple frequency components, right? So that is the use of the spectrum analyzer. So why the spectrum analyzer coming to the picture? In the antenna design, antenna may be designed for a frequency, but the antenna is working for some other frequency or it is working for the band of frequencies, right? We want to test the antenna, right? The CRO would not be suitable. You are analyzing the frequency component. So in the laboratory experiments with the help of a CRO, we can see all the time domain signals. But for the industry, would go to the spectrum analyzer, all the frequency analysis only you are making it. What is the difference between the industry and the education system? In industry is talking in a different aspect. Education system is to design and test the frequency and we will test that whether the signal which is modulated or not. Yes, it is modulated, okay. That is for the educational purpose. But for the industry, is there any other frequencies which is not used, which is not a desirable component? You have to omit it. Is there any other frequency component is also mixed with the original component? That you have to detect and you have to remove it. That is the industry aspect. Completely these two are different. In the education system, whether output is coming or not, right? In the industry, is there any other output other than our own interest is coming, which is disturbing to our system, isn't it? So that is the problem of the industry. So you have to find what are all the fault available in the board. For that, you need the frequency analysis only. In that sense, frequency domain analysis will be most suitable for the industry, not the time domain measurements. This is the spectrum analysis. Generally, we can connect any circuit. If you have a spectrum analyzer in your laboratory, you please use that spectrum analyzer for all the experiments. In addition to the CRO measurement, we can, as a student, to make measurement with the help of the spectrum analyzer. For example, even an amplitude modulation or frequency modulation, what are all the frequency components are present. We can adjust the floor level, noise floor level, and you can easily get how to measure the spectrum analyzer measurements. There is a very simple available in the YouTube itself. You can measure the complex signals, demodulated signals, amplitude versus the frequency measurements. We can easily study. See, this marker is showing that because nothing we are going to do with the help of these screen and all, everything is written on it. Marker is marking which is the peak signal and what is its power level. You see, why I am showing this is one is all the measurements will see it in the dBm, because the connector which is with respect to the 1 milliwatt only. So it is showing it is dBm, and the frequency is also, if you select a marker, this will pick up a peak signal and it will show it on the reference. These are all the measurements, and I want to show it to you network analyzer. These are all the signal analyzers. Because the time would not permit to discuss all. Let me show you. This is a signal analyzer. Yeah. This is the network analyzer which will be creating an return loss measurement, Smith chart measurement, phase measurement, VSWR measurement, everything that we can measure with the help of the network analyzer after the antenna design. So what would be the closed loop is, first we have to calculate the length, width of the antenna, what is the type of feed, inset feed or corporate feed, or it may be in simple coaxial feed. Calculate for the particular frequency all the parameters, right? Simulate it, you measure the return loss and all. Okay. Now fabricate the antenna in the laboratory, connect a connector, then come to the network analyzer. Network analyzer will test whether your simulated return loss is obtained. If the material is proper material, what would be getting in the simulated result will be available for the measurement result also. It is very same, right? Only a small deviation may happen due to the material. That you can test with the help of the network analyzer. What is its return loss? What is the standing wave ratio? What is the phase measurement and all? So S11 we can measure, standing wave ratio we can measure, then phase measurement we can measure with the help of the network analyzer. So network analyzer is a device which is used to measure all the S parameters, the two-port network. Antenna is a single port network, so that is why it is only S11. If it is a two-port network, we can measure S11, S12, 21, 22. So any two-port network can be measured with the help of the network analyzer in the microwave range of frequencies. Maybe in filter, power divider, all these structures, amplifiers, phase shifters, we can measure with the help of the network analyzer. This one network analyzer operating up to 20 gigahertz. It's a wide dynamic range, fast measurement, temperature stability is there. So this is suitable for all R&D works. Operate up to 20 gigahertz. This will operate with the help of the coaxial cable which is provided, the connector is provided multi-port test set is provided. We can test with the help of the network analyzer. So what you can do is, all the S parameters can be measured. Isolation loss, insertion loss, return loss, we can measure with the help of the network analyzer. But radiation pattern cannot be measured with the help of the network analyzer. You need to have an anechoic chamber for radiation pattern measurement. So only the radiation pattern measurement cannot be done with the help of the network analyzer. So as a part of the work, you can design, construct, simulate, fabricate, test the antenna with the help of the network analyzer. For the radiation pattern measurement, the directivity study, actual directivity of the material, you can select any anechoic chamber, go for the measurement, the radiation pattern can be studied. And a single antenna can be measured with the help of the network analyzer. But with the help of, excuse me,
Ma'am, you are now audible, ma'am.
yes, sir. Because I was in another call, so that is why I muted.
Okay, ma'am.
So in addition to the network analyzer, as a signal analyzer also will measure the S parameter, and also all the signals like the spectrum measurement signals we can measure, and also the filtering signals, EVM signals, error vector signals also we can measure with the help of CXA signal analyzer. So this would be suitable. Generally, if we design an antenna, we will have a curiosity to find whether the antenna is transmitting the signal or not. So network analyzer will test whether the antenna is working or not, right? When the antenna measurement in the network analyzer return losses less than minus 14 dB, antenna is proper. But the signal analyzer will check whether the antenna is transmitting our signal. For example, a textile antenna, biomedical antenna, for any antenna for biomedical application, we have fabricated, right? Simulated, fabricated antenna is working, that is tested with the help of the network analyzer. Next part is whether my antenna is transmitting any biomedical signal or not. I want to test that. So that we can go for EXA or CXA signal analysis. For example, this signal analysis. What this will do is, it will, you can create your own any signal, biomedical signal, for example, EEG signal. Any EEG signal you can download a signal and we can feed it to the device, and you can transmit that EEG signal with the help of your antenna. You can transmit signal and you can receive the signal with the help of the same signal analyzer at the other end. So you need two signal analyzers. One is for the transmission, another one is for the reception, right? So one signal analyzer will transmit your biomedical signal, another signal analyzer will receive the biomedical signal. So by that sense, you can understand what is transmitting its signal and it is receiving the signal. Now the problem will be okay that yes, the antenna design is working for biomedical applications, that we can understand. Then the radiation pattern, there is no other go, we have to go for the semi-anechoic or fully anechoic chamber. We have to go and measure the radiation pattern measurements. For the laboratory also, for some of the colleges may have its radiation pattern measurement, but all are working for lower range of frequencies, not for the higher range of frequencies. In PSNA College of Engineering Technology, Dielectric, we have a signal analysis. All the equipments I am showing to you, all the microwave solutions, these are all available here for the measurement. The testing, fabrication part is also available. Signal spectrum analyzers, signal generators, then power meters and power sensors, all the test accessories, a fabrication tool, and the handheld network analyzer. This one is a handheld. Any point we can take this handheld tool with the, have it in hand, then we can measure and come back. So this will be suitable up to 14 gigahertz. We have the facility. We can measure all the types of antenna tests and all under 14 gigahertz. We don't have greater than 14 gigahertz. So millimeter wave measurements cannot be done here. Up to 4G the measurements, up to 14 gigahertz we can measure with the help of the network analyzer in hand. So these signal analyzers, spectrum analyzers, LCR meters, we can go for the RF testing and measurements. All CXA, this EXA would be suitable up to the 14 gigahertz measurement only we can make it. So these devices and all would be suitable for industry. Industry measurements also we are making it. We can connect through internet and also we can measure, we can take the signal. So these higher end equipments, RF measurements, each and every devices will work as a PC. We can mail the signal, download the signal, we can copy it in a pen drive, we can transmit with the help of the network card available, LAN is available, and we can connect up to with the help of the network connection. We can connect 10 equipments as a single hand, and we can operate these devices from the mobile phone. So in the mobile phone we can install a software and we can make an app. For that we can operate those devices in remote. So from home I can operate, or you can operate my device from your side. You can operate, you can control my front panel of the equipment, and you can operate the equipment. You can take the output also, that is also possible. That is the range of the RF measurements. So because why these facilities available is, generally all designs would be better for the standard when it is tested for continuously 48 hours minimum. So we cannot sit in front of the panel for the 48 hours continuously. We can just on the equipments, switch on the equipments, connect to the internet with the IP address, then we can close the lab. We can operate with the help of the mobile phone, all the equipment. We can take measurements at any particular point. If there is any burst signal is appearing on the screen, we can stop and measure. Whatever the thing you can do, switch off, on, everything you can do with the help of the mobile phone. That is a plus point of all the Keysight equipments we have. So I think very overview of the antenna design and basic formulas for the biomedical, especially biomedical applications. For the simple textile materials can be selected, and what are all the materials available in the internet I have shown to you, and what are all the antenna measurements that can be done with the help of the RF equipments I have discussed with you.